Good morning to everyone. So I am Dr.S.Narayanan, Associate Professor of Mechanical Engineering from SNS College of Engineering. Today we are going to see an important relations in applied thermodynamics, that is pressure, volume, temperature relations for an isentropic process. So before we begin, so you have to know what is isentropic process. So it is a process which follows the law PV power gamma equal to constant. So what is gamma? Gamma is nothing but ratio of specific heats, that is Cp divided by Cv. Gamma is nothing but Cp divided by Cv, right? So this ratio of specific heats. So it is a law which follows pressure into volume power gamma equal to constant. So this process can either be compression or expansion. So if in this direction, we can call it as expansion. So if the process follows the opposite direction, we can call it as compression, right? So a reversible adiabatic process is a process in which there is no heat transfer from system to surroundings and there is no entropy generation. That is, the change in entropy remains constant. So it is an insulated system which has no heat exchange with surroundings. Example can be our flask, and reversible, no friction, unrestrained expansion, and other irreversibilities. So the process follows ideal gas law. So we are going to formulate pressure volume, temperature volume, and temperature pressure relation for this isentropic process. So first, to begin with, we will see pressure volume relation. So you all know isentropic process follows the law PV power gamma equal to constant. Hence, the temperature pressure volume relation is P1 V1 power gamma equal to P2 V2 power gamma. So this is the pressure volume relation for an isentropic process. So the next, we have to derive temperature volume relation. So the temperature volume relation, we all know for an isentropic process, PV power gamma equal to constant and P1 V1 power gamma equal to P2 V2 power gamma. Here we have two variables, that is pressure and volume. So we need temperature volume relation. So we are in need of temperature volume relation. So we have to replace this pressure with temperature. So for that, we are going to employ perfect gas equation, that is PV equal to M into R into T. This is the perfect gas equation. Therefore, we are going to write pressure in terms of temperature and volume. So P is equal to MRT divided by V. So we are going to substitute this value of P in this equation. In this equation, we are going to substitute this value of P. So the equation will become MRT1 by V1 into V1 power gamma equal to MRT2 by V2 into V2 power gamma. So this MR and MR are constant, so they will get cancelled out. So the remaining will be T1 into V1 power gamma divided by V1 equal to T2 into V2 power gamma divided by V2. So here, so V1 power 1 and V2 power 1. So this power will go, when we take this to numerator, it will become V1 power minus 1 and we can combine and write as below. So T1 V1 power gamma minus 1 equal to T2 V2 power gamma minus 1. So this equation is called as temperature volume relation for an isentropic process. So this equation gives the relation between temperature and volume for an isentropic process. That is T1 V1 power gamma minus 1 equal to T2 V2 power gamma minus 1. So this is the temperature volume relation for an isentropic process. So next is temperature pressure relation. So again, for an isentropic process, PV power gamma equal to constant, P1 V1 power gamma equal to P2 V2 power gamma. So now we need temperature and pressure relation. So we have to replace this volume with temperature. So volume should be replaced with temperature. So PV equal to MRT and V is equal to MRT by P. So we are going to substitute this instead of volume in this equation. So the equation will become P1 instead of V, we are substituting MRT by P. MRT1 by P1 whole power gamma equal to P2 into MRT2 by P2 whole power gamma. Now, next step, we are going to split these powers. So we are going to incorporate power into each and every term in this equation. So P1 into M power gamma, R power gamma into T1 power gamma divided by P1 power gamma, which is equal to P2 into M power gamma, R power gamma into T2 power gamma divided by P2 power gamma. So here, this M power gamma and R power gamma are constant. They will get cancelled out. They are common in both the sides. So they will get cancelled out. So remaining will be P1 into T1 power gamma by P1 power gamma and P2 into T2 power gamma by P2 power gamma. So here P1 power 1 and P2 power 1. So when this P1 power 1 goes to denominator, it will become P1 power gamma minus 1. Similarly, in the right hand side, P2 power 1 by P2 power gamma will become in the denominator P2 power gamma minus 1. So T1 power gamma divided by P1 power gamma minus 1 equal to T2 power gamma divided by P2 power gamma minus 1. So in the next step, we will group all the temperatures to one side and pressure to other side. It will become T1 power gamma divided by T2 power gamma equal to P1 power gamma minus 1 divided by P2 power gamma minus 1. So now, numerator and denominator are separately having power, so we will combine them. So T1 by T2 whole power gamma equal to P1 by P2 whole power gamma minus 1. So this gamma will go to this side. So the final relation will become T1 by T2 equal to P1 by P2 whole power gamma minus 1 by gamma. So we have pressure volume relation, that is P1 V1 or gamma equal to P2 V2 or gamma. So having this as base, we have derived temperature volume relation, which is T1 V1 power gamma minus 1 equal to T2 V2 power gamma minus 1. And finally, the temperature pressure relation, that is T1 by T2 equal to P1 by P2 whole power gamma minus 1 by gamma. So these kind of relations will be useful for us when we solve problems where only few variables are given and other variables are hidden. For example, if they give pressure and temperature at inlet and pressure at outlet, so we can calculate easily temperature at outlet using this relation. Similarly, with any two relations given, the third being asked, so we can use these relations easily to solve the problems, right? Thank you.